Hello everyone. We're going to take a look at this problem where we have an object that weighs 0.35 newtons in air, which is kind of a strange way to put that, has a volume of 8 cubic centimeters, and we're supposed to find its apparent weight. All right, so apparent weight, this should be something that perhaps is familiar to you. If you've ever been in say, a swimming pool and been playing around and tried to pick up one of your friends or your brother or something, you might have noticed that when the person is partly submerged in the water, they don't seem to weigh as much. And that's the idea behind this problem. Or maybe you picked up a large rock off the bottom of a creek, and when the rock was in the water, it didn't seem to weigh that much. Once you got it up out of the water, then you realized it really did weigh quite a bit. And so we're going to draw two free body diagrams for this problem. One in air and one in water. When it's in air, okay, well, there's a force upward, and then there's the weight. Okay, the weight of whatever the object is. And what's that force upward? Well, imagine that we're weighing it with a spring scale. Okay, so a spring scale has a readout. Well, it's starting to look like a clock there, but anyway. And that's measured in newtons. And it has a hook on it. And then you can take a string and you can hang your object. And it'll have a certain readout. And so, anyway, this one reads 0.35 newtons when it's in air. And so it's hanging from a string. So I'm going to call that the tension. Okay. When it's in water, then the tension's not going to be as much. I'm going to call it T star. And the reason the tension's not as much when it's in the water is that there's a buoyant force acting. The object still has the same weight. Okay, the weight doesn't change. But since there's a buoyant force, the tension changes, and the tension in the string is what pulls on the spring scale. And so that's why the weight seems to be different. All right, so what are we going to be trying to find? We're going to try to find T star. I'm going to give a positive value, and it's going to be measured in newtons. And I've already filled in some of the usual equations that we use here. And let's take a look at this density equation first. If we multiply both sides by the volume, we get density times volume equals mass. And so we can use that to solve the mass. Oh no, we're going to actually solve this for density. I stand corrected. Sorry about that. We already know the mass. Well, we know the weight. So let's put that on here as well. Weight equals mg. And so 0.35 newtons equals m times g. And so the mass, 0.35 divided by 9.8, 0.0357 kilograms. And so we're going to use that to find the density, 0.0357 kilograms divided by, well, it's 8 cubic centimeters, but we want to do this in SI units. So let's see, here's a good place, 8 cubic centimeters. There's 1 meter for every 100 centimeters. And we cube that whole thing. This is for the volume. And so 8 divided by 100 cubed. We get 8 times 10 to the minus 1, 2, 3, 4, 5, 6 cubic meters. All right, so we can put that volume here, 8 times 10 to the minus 6 cubic meters. And then we get the density of the object here, 0.0357 divided by 8, 10 to the minus 6th. And we get 4,462.5 kilograms per cubic meter. So first of all, we can see that that value is greater than, it's greater than 1,000 kilograms per cubic meter. Why is that important? Well, that means it's going to sink. And why do I even mention that? Well, if we got a density here of, say, 800 kilograms per cubic meter, that would mean it's less dense than water, and it's going to float. And then our value for T star would be 0. There would be no tension in the string, and the scale readout would be 0. The apparent weight would be 0. All right, but it is going to sink, and so we are going to have an apparent weight. And so we can go about figuring that out. Have our buoyant force equation, our second law equation here. I'm just going to say buoyant force plus T star minus the weight equals 0. And then we're going to take this buoyant force expression and we're going to put that in there. Let's go ahead and do that. So the density of the fluid times G times the volume of the fluid displaced. And in this case, the fluid displaced is going to be equal to the volume of the object. Do you remember why that is? Because the object is fully submerged. All right. Okay, the volume of the fluid displaced and the volume of the object are only equal if the volume, if the entire volume of the object is underwater, if it's fully submerged. All right. So T star equals W minus this buoyant force. And so now we can go ahead and fill this in. Density of the fluid, let's see, it just said water, so we assume fresh water. I'm running out of room here. Times 9.8 meters per second squared, and then times the volume, 8 times 10 to the minus 6th. All right, so that's not pretty, but I think you can read that. And so we get 0.35 newtons minus, let's see what that comes out to. .0784 newtons. And so we subtract, and we get 0.27 newtons. Okay, we rounded it to the hundredths place here. All right, and there's your answer. Is our solution complete? It only asked us for one thing, which was the apparent weight. We can make a note that that is the apparent weight. We also put a box around it to indicate that that was our final answer. The sign did come out to be positive. If we look back at all our units, here this does give units of newtons, and then newtons minus newtons. These newtons. Is the magnitude of the answer reasonable? Well, the only thing we can really figure out that it should be is it should be a value less than 0.35. It's not going to weigh more when we put it into water. So it's less than that, and it's not a negative value. So the magnitude does make sense. And that's all there is to that problem.